So once a set of quantitative data has been collected, it's then important that we analyse that data. What patterns or trends can we see in data to then draw conclusions from? Typically in biology, we have lots and lots of values within a data set. And if we're trying to compare, we've looked at previously where we were looking at two different meadows and the species diversity in those two different meadows, where one meadow was grazed and the other wasn't. If we were to look at all of those values within a data set, it would make it very, very difficult to find any patterns or trends and therefore make comparisons. So typically what we do when we're looking at a particular data set is try to summarize it using an average value. And as you can see, and as you know, I'm sure, there are three main ways in which you can get average values from within a data set. You can calculate the mean, the arithmetic mean. So you'd add up each of the values within the data set and then divide it by the number of values, and there's your arithmetic mean. Another way of averaging that data set is the mode. So the mode is the most frequent value within a data set. And in another video, we'll actually have a go at looking at mean, modes, and finally medians. So the median is the actual middle value within a data set. So you would write out your data set from the smallest to the highest value, and the median is that value that is bang in the middle of that data set. So there are three main ways in which you can average the data, which just means that it's less time consuming when you are trying to draw comparisons or look at patterns and trends. In biology, typically we calculate an arithmetic mean to represent the average for that data. If we were to take a data set and write out the different values, so here are on the y-axis, let's say, I don't know, we're looking at the height of buttercups in one of these fields. If we've got the height of the buttercups on the y-axis, and then we've got the different number of individuals at those different heights, what we see is when we've got continuous variation, where we've got continuous data, so that's variation that you can actually measure and quantify it. Typically you get what's called a normal distribution curve for that data set, and it's what's referred to as this bell shape curve, and it's made up from two main values. You would have a mean, so here's the mean value just here, so that's the peak, that's the top, that's the height of the curve, and then we've also got the width of the curve as well. Now what the mean value shows us, as we've already discussed, is it allows us to summarize data, and then we could compare this mean with the data set from the mean from a different data set. But what the mean value doesn't do for us is give us any indication in terms of the range of the values within the data set. And this is where we need to talk about the standard deviation for a data set. So effectively the standard deviation allows us to measure the width of the bell-shaped curve, and this then is an indication as to the the range of values either side of that mean. We'll talk about why calculating the standard deviation might be a useful thing in a moment, and in another video we'll look at how you actually go about calculating the standard deviation value. But if you calculate the standard deviation, we'll look at how you do it in a later video. If you go one standard deviation above the mean, remember this is the mean value just here. If you go one standard deviation above and one standard deviation below that mean value, that actually accounts for 68% of all of the measurements that you've taken within that data set. If you go 2 standard deviations above and 2 standard deviations below the mean value, that should actually account for 95% of all of the measurements within that data set. In order to do that, you need to have a large enough number of values within a data set. Okay, so what is the point of calculating these standard deviation values? Well, really there are two main reasons for doing this. First of all, it actually allows you to assess the reliability of the particular data set. It allows you to actually give a numerical value to the reliability. What do I mean? Well, look, I've got my two different graphs here. What can we see? Well, we can see that the graph on the top here, let's call this number 1 and let's call this one number 2. With graph number 1, we can see relatively, in comparison to graph number 2, we can see that the standard deviation is greater in graph number 1 compared to graph number 2. Well, what's that telling us? It's telling us that if the standard deviation is greater, the spread of the values around the mean must be larger. And from the investigations and experiments that we've done, we know that if you've got a very large or relatively large spread of data around the mean, that is an indication of relatively low reliability. So there is a relationship between reliability and the standard deviation. So graph number 1, there is a higher standard deviation, therefore there is a lower reliability within this data set. In comparison to graph number 2, the standard deviation is lower, it's got a smaller standard deviation, therefore the reliability is higher. And once you actually calculate numerical values of the standard deviation, then you can actually compare those values one to another. But there is a relationship between standard deviation, spread of data around the mean, and the level of reliability of that data set. So we can say that the data set number 2 is more reliable than data set number 1, for example. So that's the main use of standard deviation. The second is when you start to calculate the standard deviation for several data sets and comparing those different data sets. So with this graph, so it's graph number 3 just here. This could be the data from any experiment. So let's just say, for argument's sake, this could be let's use a classic an enzyme catalyzed reaction, and you've got temperature on the x-axis and you've got rate of reaction on the y. And what we've done then is we've at different temperatures, we have repeated the experiment, we have calculated a mean So each of those represents the mean value. For each of them, we plotted the mean values and we've joined dot to dot, and we can see the pattern or trend in those mean values. So it would appear that this temperature just here is the optimum, and we can see what happens to the rate of reaction either side. What we can do is we can show and represent one standard deviation on a line graph, and we represent it using these vertical lines, and then we just draw a horizontal line across the top. This line above the mean represents +1 standard deviation, and this one represents -1. So it's just a different visual way of representing the standard deviation for a particular data set. Okay, well, why do that? What it allows us to do then is to look at the difference in standard deviation values between data sets. And on our syllabus, what they want you to do is to look at whether error bars, so remember an error bar is a standard deviation but just in visual form. They want you to look at the error bars from each of these data sets and consider, are they overlapping with one another? Because if they are not overlapping, so this is important, if they are not overlapping, what that means is that the difference between those two mean values, so let's look at A and B just here. If the error bars are not overlapping, and you can see that they aren't here, what that means is that there is a significant difference between those two mean values. They are different to one another. Therefore, as the temperature increases from A to B, we can see that there is an increase in temperature. It is a significant increase, and when we do our stats topic, we'll see that significant means not due to chance. So there has been an increase in the temperature that's not due to chance. If, however, if data is significant, then you can be confident in that trend. Yes, as I increase from this temperature to that one, there is a significant, in this case, increase in temperature. If, however, error bars, remember error bars are just showing the standard deviation, if there is overlap between error bars from data sets, what that is saying then is that the difference between those two mean values is not significant. So look at C and D, and for that matter E. We can see that between temperatures C and D, there's overlap between the error bars. What that means is that within those range of values within each of those data sets, some are the same, and the same here at the bottom here. So what does that mean? It means then that if you do have overlap and you do not have significant differences, in this case the mean temperatures, how can you be confident in that the pattern or trend, which appears initially to be that the rate of reaction is decreasing? Well, if you have got overlapping error bars, what that is telling you is that you've not got significant differences in those mean values, in which case you can't be confident in that overall pattern or trend. As I said before, what we'll do is actually have a look at how you go about calculating the standard deviation in a later video.